Today's podcast deals with heating curves, specific heat, heat of fusion, and heat of vaporization. It actually falls underneath a topic called thermodynamics. So I'm going to fool around with a different background here. So we're going to deal with thermodynamics. And you'll have to let me know if you like this pen or not. Now the first part of this deals with heating curves and cooling curves and talks about phases of matter. So if you'd like to fast forward through that and go towards the middle of this, then you can learn about specific heat and heat of vaporization and heat of fusion. So if you look, phases of matter, they're solids, liquids, and gases. A solid holds its shape, it has a fixed volume. Liquids, it takes the shape of its container. If I pour a soda in a container onto the floor, it still has the same volume, but it takes the shape of the floor. And gas has no set volume and no set shape. It takes the shape and the volume of its container. As you can see, solids are organized, liquids are a little more spread out, and gases are crazy. So, you know some terms here. If I go from a solid to a liquid, that's called melting, and I have to absorb energy. I have to actually take energy in to overcome the attractions between my molecules. Here, this is called freezing. And energy is actually released when it snows and there is no cold air blowing. When a liquid goes to a solid, it's actually going from a crazier state. This has more energy. It's less organized. So it actually loses energy, and the air actually warms up. So this is organized. So it'd be like a bunch of fish, a bunch of sardines in a can. They're super organized. The fish can twirl around, they can flip their tails, they can hit the fish next to them, but there's not much movement because all these fish are stacked on top of each other. Now in this one, what's happening? This is like a square dance. Okay, in a square dance, what's happening? There's some order. People are do-si-doing, some people are holding arms, some people are moving around. It's a little crazier. And a gas is like a bunch of balls going all around the room, like a super ball, a bouncy ball. All right? And so, let me erase this for a second. So we said that this was melting, and this was freezing. Okay? And what's true going this way? For liquid going to a gas, that is evaporation. Right? You cause something to boil, it evaporates. And in this direction, it's called condensation. So these are phases or states of matter, solid, liquid, gas. There's also plasma, but we don't really deal with that in the lab. That's like lightning, the sun. We don't really deal with that. So we need to know what the difference is between heat and temperature. Heat, well, let me give you an example. Let's say I have a tiny little teacup. I have a big old-fashioned bathtub. And they're both full of water. And I put a thermometer in both of them. And on that thermometer, oh, that's not a good color, is it? Oops, sorry. Sorry about that. Come on. There you go. So I'm going to put a thermometer in there. No. I'm going to put a thermometer in there. I'm sorry. Here we go. I'm going to put a thermometer, and on that thermometer it reads 100 degrees Celsius. And on this thermometer it reads 100 degrees Celsius. What's true about both of those samples of water? Well, they're both 100 degrees, so they're both boiling, or getting ready to boil. Right? Water boils at 100 degrees Celsius. They're both water. What's true? I have more water here and I have less water here. So in reality, this has more heat. It has more stuff, more matter. So there's more molecules moving around. This has less stuff, so less heat. So what is heat? The total kinetic energy. And what's kinetic energy? Energy of motion. So I would agree that in this sample of water, there's lots of molecules that are moving all over the place. In this sample, they're moving all over the place, but there's less. I would rather have you pour this teacup on me than pour this whole bathtub on me. So total kinetic energy is heat. Temperature, how's the thermometer actually hurt? How's it work, rather? Sorry. So you have this, I'm thinking hurting because of the water. If the edge of this tip of this thermometer, the water molecules hit it, then the average kinetic energy, the average motion, is what the temperature is. Not all the molecules in that bathtub or in the teacup hit that thermometer. Only some of them do. So temperature is average kinetic energy, and heat is total. So let's look at heating curve. So it's true, you have a solid, a liquid, and a gas, and there's an organization. You can see the freezing, melting. And so this is a curve that shows what happens when I take a solid, and I'm going to warm it up. It's going to melt and form a liquid. So think of water. This is ice. This is liquid water. We call it water, right? And this is steam. So what happens when ice melts? It forms water. So if this was water, this would be 0 degrees Celsius. And along this line right here, it would be ice that would warm up. I don't know, let's say this is -20. It would warm up. It would reach 0 degrees. The ice would melt. It would form cold water. It would all be a liquid. Then slowly that liquid would warm up and reach the point where it could evaporate, okay, boiling or evaporating. Water doesn't boil if I leave it on the counter. I can make it boil, but it evaporates, so that's really not a good term there. Then what happens? That water in the pot, if I'm boiling water and it's evaporating, it takes time. And slowly but surely, all of it turns into a gas, and then I have steam. Now, if you go in this direction, it's cooling. So you have a heating curve going up and a cooling curve going down. Let's look at energy. On these plateaus is potential energy. Plateau energy, potential energy. Here, I can spell, overcoming attractions between molecules is what's occurring. So if I'm talking about ice, right, if this was 0 degrees and this was ice melting, all along this line from when all that sample of my ice actually reaches the point of 0 where it can melt, and then all of it forms a liquid, that whole time period, right, the heat energy, that whole time period, because I can label this time too, this whole time period, it's overcoming the attractions between the ice particles, the ice molecules, the solid water molecules. Solid water, right? Solid water is ice. So what's happening here? Here I have liquid water, completely liquid water. It's all really hot. It's all ready to start evaporating. And what's true here? It's overcoming the attraction from being a liquid so that it can form steam. This also is potential energy. It's overcoming the attractions between the ice molecules. Here, ice molecules. Here, water molecules. Now, what about the other lines? Okay, and actually, let me redo this for you. Here's potential energy, so we're clear. Potential energy is here. Potential energy is here. On these areas, here, here, and here, and I should actually use a different color. So let's use red, red, and red. Those are kinetic energy. Think of it like climbing a hill, right? To climb a hill, I need to gain energy to go from a lower point to a higher point, to a lower point to a higher point, from a lower point to a higher point. This is called a cooling curve. Oh, and look, they have it labeled for us. So cooling means I'm starting out at a higher temperature, right? This is ice. How do I know it's ice? Because the melting point or the freezing point right, is at 0 degrees Celsius, and this actually should say degrees Celsius over here so I know. And here at 100 degrees is the boiling point or condensation point. So what's true? Here I have steam, okay, and it's cooling down to 100. Then, after that kinetic energy is given off, potential energy, all the water vapor is attracted to each other and then forms liquid water, cools off, right? That's kinetic energy, until it reaches 0, and then slowly but surely all the ice little particles start forming, and all these attractions form. And then I form really super cold ice, right? Like Antarctica, your freezer. So notice where the kinetic energy is, right? Kinetic energy, kinetic energy, kinetic energy, going up and down a hill. And potential energy is on a plateau, overcoming or forming attractions between molecules. Here's a definition you have to know. Specific heat. The amount of heat energy needed to change the temperature of 1 gram of a substance by 1 degree Celsius. So what's that mean? That means if I want to heat something up, the amount of heat energy I need to heat 1 gram of that substance and change it by 1 degree is the heat energy. So I can't say that aluminum heats up easier than water. If I do, I've got to compare it by 1 gram, a certain amount. So you have to have a gram of aluminum and a gram of water, right? The same amount, 1 gram of a substance, and you're going to change it by 1 degree Celsius. Can't really see this really clearly. If I can stretch it on here. I think I can. Yeah, how about that? Not wonderful, but you get an idea. So what is this? This is a specific heat capacity table. And if you notice, I've got water, and the value here, I'll write it, is, is 4.184. And the units are joules per gram degrees Celsius. Let's look at our specific heat for a second. What's our definition? The amount of heat energy. That happens to be measured in joules, after a guy named James Joules. We abbreviate with a J. It's the amount of joules needed to change the temperature of 1 gram of substance, or per 1 gram, and to change it by 1 degree Celsius. This is the unit that goes with specific heat. So it's amount of heat energy per every gram to change it by 1 degree Celsius. How handy that the definition is the label. So let's look at this. Water is 4.184. And I'm sorry I actually stretched that because let's look at this for a second. If you look down here, mercury is really low, 0.14. So this is water, and that's how much energy it takes to raise 1 gram of water by 1 degree Celsius. And mercury's 0.14 joules per gram degree Celsius. For every gram of mercury, this is liquid water, it's way easier to heat it up. So why do we used to use mercury, and sometimes if you still have an old thermometer, why do we use mercury in a thermometer? Because it's easy to heat up. So let's look for a second. Look at aluminum. Aluminum has a specific heat of 0.9 joules per gram degrees Celsius. It's aluminum. So what's true? Water is very hard to heat up. It's difficult to heat up. That's a good thing. If it was easy to heat up, look what happened to lakes and ponds in the summer. Or you boil. What about aluminum? Aluminum is not as hard to heat up as water. So what do we use aluminum for in our life? Aluminum pots and pans to bake with, right? Okay, and you would not touch a piece of metal in the hot sun in the summertime because it heats up. So question, look at iron. Iron has a specific heat of 0.444 joules per gram degrees Celsius. Which one heats up easier, aluminum or iron? Iron does because it's got a lower specific heat. Aluminum has a harder time heating up, whereas mercury, well, that takes hardly anything. And look at gold. Gold is 0.129, one of the lowest specific heats we know. It's super easy to heat up. Okay, so which would you rather touch if I put it in the sun? A gold plate or a aluminum plate? I'd rather touch the aluminum. It's going to be hot, but gold is going to be super hot because it's easy to heat up. Way easier than aluminum. So, of course, there's math involved. And this is the equation. You can remember it however you like to. You can remember Q equals mc delta T. You make a little ditty out of that. Q equals mc delta T. Okay? So what's Q? It means heat energy. And what was our heat energy again? We measured that in joules. Mass. Well, we measure mass in grams. Right? Abbreviated with a G. I'll write it out. Grams. Specific heat. Well, what were our units? The amount of heat energy in joules per 1 gram per 1 degree Celsius. By the way, sometimes they call this CP or CS. It depends, but you'll see that. And temperature change, well, that's always final minus initial. Or what you end up with, right? Your final minus what you start with. And that's what you're going to use to solve specific heat problems. So let's look at this. Oh, this is a bad color. All right, well, we'll go with it. Okay, I just want to use this template again. So, really faint here. It says, find the heat energy needed to change 10 grams of water at 2 degrees Celsius to 20 degrees Celsius. So, what do you know? This is Q equals mc delta T. So what's that mean? That means joules. This is really bad, isn't it? I'm sorry, guys. Let's use white. Nope. Sorry. So we'll use white. All right? So I need to find the heat energy. I need to find Q. Now, unfortunately, this is like the physics and deep chemistry. Let's take it into our English here. We have joules equals mass in grams times specific heat, right? Times change in temperature, which is final minus initial for degrees Celsius. Sorry. So now what do I know? I know I'm trying to find heat energy. I don't know Q. I do know I have mass in grams, so I have 10 grams, right? And what's the specific heat for water? Well, let's go back and look at that chart. Right, I know it is, but I want to show you so you can look it up. On the chart, it was 4.184 joules. Right, it was this right here. I looked it up on the chart right here. That's something you might not remember. So, I'd go 4.184 joules per gram degrees Celsius. And then I do final minus initial. What's my final? What do I end up with? I end up with 20 degrees. What do I start at? Right here, I start at 2. So minus 2 degrees Celsius. So when I do my math, what do I end up with? I end up with 10 times 4.184. And what is 20 minus 2? It's 18 degrees. So when you multiply 10 grams times 4.184 joules per gram degree Celsius times 18, then what do you get? You do it on your calculator right now. And I get 753.12. And I label that joules because that's the heat energy. Okay, look at that for a second so you know, because that is your equation. All right? Let's do another one. Find the heat energy needed to change 10 grams of water. Well, we just did that. Sorry. Okay, there's my specific heat. So you can see that water is 4.184. Let's do this one. A 15.75 gram piece of iron. So what do you know? You know you have a mass, right? So I'm going to write Q equals mc delta T right here. And as I go through this, I'm going to go ahead and show you what I know. I know I have a 15.75 gram piece of iron. It absorbs 1086.75. What's that mean it absorbs? If it absorbs, that means it's heating up, right? And that's in joules, because I need to include my units. The temperature changes from 25 to 175. That makes sense, doesn't it? Because didn't we say it was absorbing energy? It's heating up. So I have 175, I should put this right here, sorry, 175 degrees Celsius minus 25 degrees Celsius. So when I subtract, what do I get? 150? I'm going to include these units right here because that's really what I should have included. I should have done this. Okay. And what am I solving for? I don't know specific heat. That's my x. So how do you solve? You take 1086.75 and you divide 15.75 on both sides, and you divide by the temperature change, 150, 150 degrees Celsius. And that's going to give you your x, which is specific heat, right? That's what you're trying to find. And what do you get when you do that? .46. You write 0.46 if you'd like to. And what are my units? Joules per gram degrees Celsius. And that makes sense, because what am I solving for? The specific heat. And the specific heat is the amount of heat energy needed to raise 1 gram of something by a degree Celsius. So this is for iron. So let's look and see. And granted, we're going to have a little experimental error, but if we look at the specific heat for iron, right here, it says it's 0.444 joules per gram degree Celsius. Our 0.46 we just got is pretty close. So if anything on here, our sample's iron. Let's do another one. 30 joules of heat energy are added as 10 grams of aluminum is heated. What's the change in temperature? If it says it's heated, does that mean our temperature is going to be going from a lower temperature to a higher temperature? So we're going to have a positive temperature. Okay, I'll talk to you more about that later in class. So what do we have? We have 30 joules of heat energy. Right, that's our Q, equals M, 10 grams, C. Oh, I need to know what aluminum is, don't I? So let's look on a chart. Aluminum on our chart is 0.90. See right here? 0.900 joules per gram degree Celsius. So, it's their aluminum. I'm going to put 0.900 joules per gram degree Celsius, and I want to know the temperature change. This is my x. So how am I going to solve? I'm going to take 30 and divide it by 10 and divide it by 0.9. So I take 30 joules, I divide both sides by 10, right? And I divide both sides by 0.9. Look what happens. My joules cancel, my grams cancel, and I have 1 over degrees Celsius, which means in math that flips out, and I'm left with degrees Celsius, and my degrees Celsius is 3.33 degrees Celsius change. It's about 3, sorry. Okay, I'll just check my math and make sure I'm correct. Yeah, so it's 3.33. I'm not having a very good pen day. All right? So it's a change in temperature. Let's do one more. Find the energy given off. And if you notice, I meant to mention this earlier, there's heat and there's specific heat. So be careful. Heat energy is in joules. Specific heat is in joules per gram degrees Celsius. The specific heat for water is 4.184 joules per gram degrees Celsius. Always, every gram changing by 1 degree Celsius requires 4.184 joules. So we are finding the joules. We don't know that. That's the cue. We have 30 grams. My specific heat, right? I'm sorry. I should do it like this, so I stay consistent. M, right? So 30 grams. My C, which is 4.184 joules per gram degrees Celsius, times, now look at this, there's no temperature change. I don't have a final minus initial, but I'm changing it by 20, right? It's cooling. So that actually would be a negative value, right? So my joules would actually be negative and my temperature actually be negative. They have to match. Well, again, we'll go into that later. So my temperature changes 20 degrees. So I multiply these 3 together, don't I? So what do you get when you multiply 30 times 4.184 times 20? I get 2510.4 joules. Okay, and all you're doing is mass in grams times specific heat for water, and again I looked it up on a table, times the amount of degrees I want to change it by. Now what if I wanted that in kilojoules? 2510.4. It's always in joules because Q is in joules because specific heat is in joules. What if I wanted to change that from joules to kilojoules? Joules goes down here, kilojoules is here. This is bigger. There's 1,000 in it. So I'm going to actually move my decimal over 3 places, which you know when you do your King Henry died, right? You're going to take your decimal and go 1, 2, 3 places that way. 2.51 kilojoules. All right? Yeah. That's for specific heat. If we go back to our heating and cooling curve, rewind. So on these potential energy plateaus, this is actually where heat of fusion, no confusion about heat of fusion, and heat of vaporization occur. Now what does it mean to say heat of fusion and heat of vaporization? Well, heat of fusion means how much energy it takes to melt an ice cube or any kind of solid, or how much it takes, or how much energy is given off when it freezes. How much energy it takes to evaporate something, and how much energy is given off when it condenses. So not how much it takes to boil it, how much it takes to have water that's all steam turn into more steam, or to have liquid water heat up from really cold to boiling. This is how much energy does it take to take liquid water and actually turn it all into steam? Or to take solid ice and actually turn it all into water? Or take water and turn it all the way back into ice? Or take steam and turn it all the way back into water? That's what heat of fusion and heat of vaporization are. So again, this is heat of fusion, and we call it delta H of fusion, heat of fusion, and this is delta H of vaporization. If you can imagine, ice is going to take the same amount of energy to melt or to evaporate. If you have water, I can look it up. So the heat of fusion can be given in joules per gram, or it can be given in joules per mole. So let's do one. Okay, so this is your equation, heat of fusion. How much stuff you have, the mass, times the heat of fusion. So this is Q, our good old friend Q, isn't it? Let me change my color. So this is Q. Ah! Yeah. There we go. All right, so Q equals, let's say I've got a problem and I have 10 grams of ice. So I've got this ice, it's 10 grams, and I want to melt it. I want to change it from ice to liquid. So 10 grams of ice, how am I going to change it to liquid water? How much energy is it going to take? Well, what do I have? I have 10 grams. And I have to look up in a chart in a book, 340 joules, there's our friend, our heat, right? Our heat energy, how much energy it takes to heat that ice cube up until it actually all forms liquid water. It's that many joules per gram. So for every gram I have, it takes 340 joules. What do I have? Oh look, I have 10. So I'm going to take 10 grams times 340 joules per gram. Or you can use your good old train tracks. I have 10 grams. I don't want grams, I know how many joules I have, and look what I have here. 340 per every 1 gram. So, what's 10 times 340? That's how much energy it takes to melt 10 grams of ice. For every 1 gram of ice, it takes 340. If I had 2, it takes twice the amount. 3 times. So if I have 10 grams, it's 10 times that. Heat of vaporization. Well, if you think about water, it's easier to melt ice than it is to take water that's a liquid, right? We write water with a liquid like this, to go to gas, right? To steam. So what's going to happen? Or not even steam, just a gas. It evaporates. So what's it going to do? What's it going to take? Well, the heat of vaporization is 2270 joules per every gram. Now look at the difference, right? For ice, it was 340 joules per gram. For water to go from a liquid to a gas, it's 2,270 joules per every gram. So let's go with that 10 grams again. The 10 grams of ice turned into a liquid in our last slide. And now we're going to take it and we're going to turn it into a gas. So let's erase this. And what's our equation again? Well, heat is Q, right? A little Q. So what is Q here? We're trying to find it. So my problem is, how much heat does it take? Well, I have 10 grams, right? Don't we have 10 grams before? 10 grams of ice turn into 10 grams of liquid, right? If you have 10 grams, you're still going to have 10 grams. So here now I have 10 grams of liquid, and I have 10 grams of gas. So 10 grams times 227 joules per every gram, right? Per every 1 gram, that's what that is. So doing train tracks, if you like, 10 grams of water, liquid water, to turn it into steam, just water vapor, Okay, for every gram, that's what it's going to take. Okay, and it's going to be 227000. Excuse me, 22720 joules. And that's going to be a big amount of joules. So sometimes we report it in kilojoules, which would be 22.7, right? And we'll worry about significant figures later, but that's how many kilojoules. Makes it more manageable, a little better number to deal with. Now, last thing. What if I want to find out how many moles? Because that's sometimes how it's given to you. Heat of vaporization, remember in the last slide it was 2270 joules per gram? Well, sometimes it's given to you in kilojoules per mole. So 6.02 kilojoules per 1 mole is the heat of vaporization for water. So let's say I have 140.8 grams of water. I want to know how much heat energy is required to turn liquid water into water vapor. So what do I know? I know I have 140.8 grams. My problem is I know kilojoules, but it's in moles. So I need to change grams of water, right, this is water, to moles of water. So we use our mole map. If you add up hydrogen, which is 1.01, and oxygen, which is 16, and there's 2 of these, so it's 2.02. Your mass of water is 18.02 grams. And what do I know? That for every 1 mole of water, it takes 6.02 kilojoules, right here. So let's go ahead and solve that. On your calculator, go ahead and do that. And if you work it out, I get, so I have a funny calculator. You're going to be able to do this faster than I am. 47.03, that's what I get. Do you? I had something else written down on my paper. So that's kilojoules. So how do we turn that into joules if we wanted to? When we go that way 3 places? 47030 joules. So think about that for a second. Look at what your value was for ice. Of course, it wasn't the same amount, but it takes a heck of a lot more energy to vaporize water than it does to melt ice. And that is it.